So up to now, we've been doing integration with area under a curve, where it basically looks like you've got some function f of x, and we delineate two spots a and b on the x-axis, and we look at the area underneath this curve with the curve at the top, and these kind of boundaries here, and it stops at the x-axis. But what if we wanted a different kind of area? So what if it was like some weird kind of balloby-shaped area like this, and we wanted to get this area? Well, it turns out there is a way to use calculus to be able to figure out this area. But a shape like this is a little bit beyond what we're going to learn in standard AP calculus. This is more of a Calc 3 kind of thing. But there is still something fancier we can do, and that's when you have a region that kind of looks something like this, where you've got a function here on top, and instead of going all the way to the x-axis, we just kind of have some other function here, and we cut it off, and it looks like this. So how do we do an area like that? Well, there's basically two ways to think about it. So one of the ways is to imagine these little pieces of straw, these varying lengths. We're going to integrate these different lengths together, so add them all up. So we need to figure out how long is this individual piece right here. Well, it's this entire height right here, so in order to the y-coordinate of this point right here, so that's f of x. But we have to take away this blank part out here. So that's the part that's governed by the y-coordinate of g at that same spot. So to get just this black part, we have to take the red length, take away the green length, and that gives you that black segment. So it's f of x, take away g of x, and then we have to add all those up. So that's what we'd be integrating from a to b. So that's one way to think about it, just adding up all these black segments. But there's also another way to think about it, and it really just amounts to the same thing, but just conceptually maybe a little bit different, is if we want to find the area here, we can say, all right, let's take the old-fashioned way we were doing, we just ignore the green f of x on the bottom, just look at the red f of x on the top, look at its area the normal way, going all the way to the x-axis. Of course, we don't want all of that, we only want this part right up here, so rather than looking at only the red area, the integral from a to b of f of x dx, let's take away the g of x part. So that would be subtracting off the integral from a to b of g of x dx, and what's going to be left? Well, just exactly the area that we want. Observe, though, that this way of expressing it is actually the same as what we observed before, because by one of the properties of integrals, we can just put that together into one single integral and say, oh, it's just the integral from a to b of f of x minus g of x dx. Alright, well, a standard way that you might see it is sometimes without these specific boundaries given. So when you have these specific boundaries, you get these kind of vertical right and left edges here. But a common kind of situation that occurs is we just say, hey, let's find the area of a region which is in between two curves. And we don't necessarily give you the bounds. So maybe we got some crazy function here and another one here. And we want to say, hey, what's the region in between these two curves? So we're not looking at all the way to the x-axis. We just want this part right in here. So notice this is the region, the finite region bounded here. We don't look at the region out here because this would be infinite. Same thing on this side. We're only looking at this part right here. So what we need to do is figure out the bounds of where to kind of put those quote-unquote vertical lines, except there are no vertical lines this time. They kind of come to a point. So what we need to do is figure out the intersection if we want to compute that finite area. And we know how to do that, right? So this is now just basically an algebra problem. So if you want to find where two curves intersect, you basically set them equal to each other and solve for the x, which makes the y coordinates the same. Well, let's look at a particular example. So let's suppose that f of x is x squared plus 3x plus 5. So we know it's going to be a parabola shape. By the way, I'm not referring to this picture over here. This is just a brand new problem. So that'll be our f of x, and let our g of x be x cubed plus x plus 5. Now, one thing I want to point out is that when you compute the area between two curves, so if you look back what we were doing, we were always doing the top curve take away the bottom curve. So it matters which one's on top and which one's on the bottom. But in this particular case, if you think about it, this is a parabola, this is a cubic. In fact, I'm just going to jump to the calculator so we can take a look and see what this looks like. So you can see that, hey, sometimes the blue one is on top, that's our parabola here, and sometimes this cubic curve, the red one, is on top, because over here it's on top, but over here the cubic, the red one's on the bottom. So we're actually going to have to do this in two separate pieces. Now if you don't do it in two separate pieces, what you're going to have is this area canceling out with this area. You're not going to get the total area bounded between the two curves. But our first step is to figure out, well, where are these intersection points? So we got to set these two things equal to each other, and that's what I've done over here. So x cubed plus x plus 5, when is that equal to x squared plus 3x plus 5? Well, the first thing to do is just kind of realize that, hey, those plus 5s go away. We can just cancel those, subtracting 5 from both sides. Let's scoot everything over to one side. So x cubed minus x squared minus 2x equals 0. Hey, they both have an x in common, which we can factor out. And then we can recognize this and say, oh, this, do a little backwards foiling factoring, x minus 2 times x plus 1. So in the end, we've got three different places. X can be 0, or x can be 2, or x can be negative 1. And notice that matches what we see in the graph here. When you eyeball it, it kind of looks like, hey, they were intersecting right on the y-axis there. We also could have looked at the equation and realized these both had the same y-intercept at 5, but this is just going through the algebra to realize that indeed is the case. Alright, again, I just want to emphasize the key thing to remember for these kind of area between two curves kind of problem is that when you set it up, it always has to be set up as the equation of the top curve subtracted by the equation of the bottom curve. So top minus bottom. And if that changes hands, like it does over here, then you have to set it up as two different integrals. So we're actually going to set this up as split up into two different regions. First we'll do this region over here, which as we just figured out goes from negative 1 to 0, and we have to do the top curve, take away the bottom curve, which in this case the top curve is the red cubic, take away the bottom parabola in blue. Then we have to add on this region right here, so that area is represented by the integral from 0 to 2 of top curve, which in this case is the blue one being the quadratic, take away the bottom curve, which is the cubic in red. So now we just have to subtract these off, but we kind of already know what this subtracted is because it's exactly what we had done when we were finding the intersection. So it's just going to be x cubed minus x squared minus 2x over here, integrating between negative 1 and 0. And this one, we don't actually have to go through the same subtraction again because we know it's just going to be exactly the opposite of what we got here. So if before here was x cubed minus x squared minus 2x, we just change all the signs. Minus x cubed plus x squared plus 2x. And now it's just a matter of doing the integration. So this is just simple direct power rule, nothing fancy. So we just integrate piece by piece. So it's add 1, divide by the new exponent. Just keep on doing that. And we're integrating that one between negative 1 and 0. So that's that integral. And now we do the same thing with the second integral. And again, it's just going to be exactly the same answer, but the signs will be changed. So we're going to add the second region being negative 1/4 x to the fourth plus 1/3 x cubed plus x squared, and this time we're going between 0 and 2. So using our stick notation, that means first we stick in the top, then subtract what we get when we stick in the bottom. Well, just by inspection we can see that if we plug in 0 in here, this whole thing is going to come out to be 0. And then we have to subtract what we get when we plug in a negative 1. This gets perhaps a mite tricky with all the sign changes, but we know a negative number to the fourth power because this power is even, it's going to be 1, so 1/4. A minus 1 cubed becomes a negative 1, which combined with this negative makes it positive, and a negative 1 squared becomes positive 1 with a minus in front here, so that's a minus. Don't forget there's a minus in front of all of this, but we'll deal with that after we do the second sticking. So with the second sticking, first we plug in 2, subtract what we get when we plug in 0, and we plug in 2, so negative 16/4 plus 8/3 plus 4, and then again when we plug in 0 you're just going to get 0 in the end. And now I would actually just recommend doing this on a calculator rather than risking making a mistake, but when I do it I believe we get 37/12. So that is the area between the two curves, these two yellow parts. And that's it. That's how you do that kind of area between two curves problem. Alright, I want to point out mathematically, how do you say the whole top minus bottom thing, right? So, I mean, how does the formula know that F is supposed to be on top or that G is on the bottom? So, let me show you how you can actually express this mathematically. So, suppose you've got some crazy function F and another function G here, maybe they change places a few times, and you want to know, hey, what's the area of the region bounded by these two curves. So again, we're only talking about the finite region, just these two weird blobby shapes, not any of this stuff that's out here or out here. So if you want this area, so we want to know, hey, let's add together all the lengths of these individual pieces of straw here. Well, if you want to know these individual lengths, well, sometimes it's f minus g, and sometimes the length is g minus f. Well, how do you know which to do? Well, what you can do is you can say, just always do f minus g, but then take the absolute value of it, right? So that way you're always getting the actual length of the stick. So the actual definition of a region between two curves, going from a to b, is just the integral from a to b of the absolute value of f of x minus g of x dx. So the reason why we had to break it up into two different integrals is that sometimes we did f minus g, the f was on top and it's positive, so the absolute values didn't matter. But sometimes the g was actually on top, and so it was the other way around. It was g minus f. Okay? So that's why it matters where these intersections are. So you can break it up into two different integrals. But technically what we were doing before without realizing it was really just doing absolute value. So one last thing I want to point out is that when you're doing the area of a region bounded by two curves, it's independent of the x-axis. So before, we were just always saying, hey, let's do the integral of f of x without a g of x, and just stopped at the x-axis. But here, there's no reference to the x-axis at all. It's all relative to f and g. So whatever this yellowed region is, it shouldn't actually matter where it's located. So for all we know, maybe it's down here. Okay? We should still get the same answer. And if you think about it, when you compute this absolute value of f of x minus g of x, it doesn't actually change the answer. So where the x-axis is in this case, when you're looking at the region bounded by two curves, the actual position in the plane is irrelevant. So you might be used to thinking of that area underneath the x-axis as negative, but that doesn't come into play here. So if you think back to the answer we had before of 37/12, notice that's a positive number, and in fact the area between two curves when you're talking about a region on a plane must always be positive. And if you look at this definition, you can see that that makes sense, that the answer should always be positive because you're integrating something that's always positive, because the absolute value turns even negative numbers to be positive.